Hello everyone, I am Pratik Deepak Phapale from Pimpri Chinchwad College of Engineering, Pune. Today I will be presenting on the topic Error Detection and Correction, which is from Unit 3 of our Data Communication course under the guidance of Professor Shweta Devdas ma'am. So let's get started. Here's a quick look at what I will be covering today. We will start with why errors occur, then look at the types of errors, move into the detection techniques, the correction techniques, see some real world applications, and finally wrap up with a comparison and conclusion. So first, why do even errors happen? When data travels from sender to receiver through any physical medium, whether it is a copper wire, fiber optic cable, or wireless signal, the signal is constantly exposed to interference. Three main causes are attenuation, where the signal weakness or distance noise, which is the electromagnetic interference from surrounding sources, and distortion, where the shape of the signal changes during transit. The result, a single bit that was supposed to be 0 arrives as 1, and that tiny change can corrupt the entire message. This is exactly why error handling is so critical in data communication. Now, errors of two types. The first is a single bit error, where only one bit in the data changes. For example, 10110010 becomes 10010010. This is relatively rare in serial transmission. The second and more dangerous type is burst error, where two or more consecutive bits get corrupted. The length of the burst error is measured from the first corrupted bit to the last. Burst errors are far more common in real world scenarios and much harder to handle. In fact, most practical error detection methods are specifically designed to catch the burst errors. Before I explain each technique, let me clarify one important thing. Error detection and error correction are not the same. Detection simply means identifying the something new went wrong. The sender adds extra redundant bits to the data and the receiver uses those bits to verify integrity. We have three major detection techniques: parity check, checksum, and CRC. Let's look at each one. The simplest technique is the parity check. Here the sender adds one extra bit called the parity bit to make the total count of 1s either even or odd depending on the agreed parity scheme. For example, in every parity, if your data is 10111010 as 4 ones, which is already even, we append a parity of bit 0. This receiver counts the ones in the received data. If the count matches the agreed parity, no error is assumed. However, this technique has clear limitation. It can only detect single bit errors. If two bits are flipped, the parity remains the same and the error goes undetected. It also fails against the burst error. So while it's simple and fast, it's not reliable enough for the most modern systems. The next technique is checksum, which is more powerful than parity. Here's how it works. The sender divides the data into equal size segments, adds them all together, and then takes one's complement of the sum. This results in the checksum, which gets appended to the data before transmission. On the receiver side, all segments including the checksum are added together. If the final result is all ones, the data is considered error-free. If not, an error is flagged. The beauty of the checksum is simplicity with the better coverage. You will find it used in real protocols like TCP, UDP, and IP, the very foundation of internet communication. Now, the most powerful detection technique, CRC, or cyclic redundancy check. CRC treats the entire data as a binary polynomial and divides it by a pre-agreed generator polynomial. The remainder of this division is the CRC, which gets appended to the data. When the receiver gets data, it performs the same division. If the remainder is 0, no error. If the remainder is non-zero, error is detected. What makes CRC exceptional is its ability to detect all single bit errors, all odd number bit errors, and all burst errors shorter than the length of the generator polynomial. This is why CRC is used the standard used in Ethernet, Wi-Fi, USB, and even zip files. It's the industry benchmark for error detection. Now let's move to error correction. There are two broad approaches. The first is backward error correction, also called ARQ, automatic repeat re-request. Here's the receiver detects an error and simply asks the sender to retransmit. This works fine when delay is acceptable, like TCP based internet communication. The second approach is forward error correction or FEC, where the receiver has enough redundant information to not just detect but actually correct the error on its own without asking the retransmission. FEC is critical in real-time systems like satellite communication or video streaming, where the waiting for a retransmission is not an option. The most well-known FEC technique is the Hamming code, invented by Richard Hamming at Bell Labs in 1950. The idea is elegant. Redundant parity bits are inserted at the positions that are powers of 2, that is positions 1, 2, 4, 8, and so on. Each parity bit is responsible for checking a specific set of bit positions when the receiver gets the data. It recalculates the all parity bits. If there is a mismatch, the binary value formed by the mismatch parity bits directly gives the position of the error. That bit is flipped and the error is corrected automatically. Hamming code can detect up to 2-bit errors and correct 1-bit errors. It forms the basics of ECC memory used in servers and high reliability computing systems. Let's now connect all of this to real world. Error control is everywhere. Your internet traffic uses checksum in TCP, UDP and IP headers. Your Wi-Fi and Ethernet use CRC32. Your hard disk and SSD use ECC memory based on Hamming codes. Satellite communications relies on powerful FEC method like Reed-Solomon and turbo ports because retransmission from space is simply not feasible. Even the CD or DVD you play uses Reed-Solomon to recover the scratched or corrupted data. Your mobile network 4G or 5G uses LDPC codes, and every time you extract a zip file, CRC32 verifies it was corrupted during download. Error control is truly the invisible backbone of the all digital communication. Here's a quick comparison of all techniques we discuss. As you move from parity to checksum to CRC, the detection capability increases, but so does the complexity. And when you move to Hamming code or Reed-Solomon, you gain correction ability, but at the end, the cost of even higher redundancy and processing. The general thumb rule is use detection with transmission when the delay is acceptable and use forward error connection when real-time delivery is critical. To summarize, errors in data transmission are unavoidable due to noise, attenuation, and distortion. They can be single bit or burst errors. Techniques like parity, checksum, and CRC help us to detect these errors. Hamming code and Reed-Solomon go a step further and connect them. The choice of technique depends on the system tolerance for the delay and the overhead. As our data demands grow, robust error control by only becomes more important, not less. Now, some of the questions people generally have here for the same class. Feel free to think about them. Question 1. What is the difference between error detection and error correction? And why can't all systems use the error correction of all the time? So, think about it. Now, the key reason is overhead. Correction requires far more redundant bits, which waste bandwidth. So, detection plus transmission is preferred in most network systems. Question second. Why is CRC preferred over the parity check and checksum for Ethernet and Wi-Fi networks? Think about it. So, because CRC can detect burst errors, which are the most common in real networks, parity misses, even numbers of errors, and checksum can miss patterns, where errors can cancel out CRC polynomials, division makes it far more reliable. So that brings me to the end of my presentation. Thank you all for your attention. I am happy to take any questions from the teacher or the class and from all audience. Put it in the comment box.